Okay, so for this problem, we are given a tank and a jacuzzi. And the tank is going to be pumping water, or water's going to be flowing into the jacuzzi from the tank, and the jacuzzi is going to be pumping the water back into the tank in a cycle. And we do know that the tank water height is 3 meters high, and the distance from the tank to the jacuzzi is 7 meters to the bottom. And we also know that the jacuzzi is held at a 1 meter height consistently. And what we're basically trying to find here is the power that's required, given that it's 100% efficient pump. Sorry. So given the dimensions, we're going to call this position 1 at the top of the tank, and then we're going to give position 2 at the bottom of the jacuzzi. Okay, so here we have our height. And yeah, so in order to really solve this equation, first we're going to have to understand the idea of a flow rate. And here we're going to say that the flow rate at position 2 is going to be equal to our area 2 times the speed or velocity 2. So our first goal is basically going to be set up an energy balance in order to solve for our V2 right here. And then we're going to plug this into our flow rate equation. So in order to do that, we're going to have to know, for an energy balance, we're going to have to say that our change in pressure over our density plus our potential energy difference plus our kinetic energy difference is going to be equal to our non-flow work per mass minus our internal energy minus our heat per mass. Okay, and this is basically our frictional heating. And for this problem, we're going to set this equal to 0 in order to solve. So now that we know that the frictional heating is equal to 0, it makes this a lot easier to solve. So we're just going to break this pressure up. So we're going to call this pressure 2 minus our pressure 1 over our density plus our, you're just going to break up our potential energy, so Z, or our height 2 minus our height 1, and then we're going to add on our V2 squared minus V1 squared over 2 and set that equal to 0. Okay, so we're going to say that our pressure is equal to 0 simply because that's at the top. At position 1 is the top of the water, so there's no pressure there. And we're also going to say our velocity, our V1, is also equal to 0. So that makes it a lot simpler. So if we're going to break up our pressure 2, we can just call that rho GH. And in this case, we're just going to say 1 meter because at position 2, we know the water level is 1 meter high. And then divide that by our density and add on our height differential times G, which in this case we know is 7 meters here and 3 meters here, so that's a minus 10 differential. And then we're going to add our V2 squared over 2 and set that equal to 0. Okay, so right away we see that these densities will cancel and we're just left with 1G minus 10G plus V2 squared over 2. So we're just going to call that negative 9G is going to, and then plus V2 squared over 2 and set that equal to 0. So we're going to add our 9G over to that side, multiply by 2, and take the square root of that. So we know that V2 is equal to the square root of 18G. Cool. All right, we're almost there with our flow rate equation. So we know that our flow rate is equal to our area 2 times our velocity 2, right? So we have that, we just need our area. And we know that it's a 10-inch diameter, so that helps a lot. So from there, we're going to convert our 10-inch into meters and then find the area. So in order to do that, we're just going to say 10 inches multiplied, there's 12 inches in 1 foot, times our 1 meter over 3.28 feet, because there's that many feet in a meter, and that is equal to approximately 0.254 meters. And then divide that by 2 to get our radius, and that is equal to 0.127 meters equals our radius. Okay, so we know that area is pi r squared, so this number squared times pi. So we're just going to say pi times 0.127 squared is about equal to 0.051 meters squared. And that is equal to our A2. So let's go ahead and plug that in. So our volumetric flow rate here is going to be equal to our 0.051 meters squared. And then times our square root of 18 g meters per second. Okay, cool. So we have our volumetric flow rate. So our next step is going to be to find that non-flow work per mass in order to plug all this into the power equation to find the amount of power. So in order to do that, let's go ahead and start on this side. Just give us more room. First, let's just redraw this really quick. So we have our tank up top. We have our jacuzzi down here. Yeah, so this is, as we know, 1 meter, and this, we're just going to draw all the way to the top actually, is 9 meters. And from there, we're going to say that this right here, from right here, up through the pump and back into the jacuzzi to position, this is going to be position 4, and this is going to be position 5, okay? So let's make another energy balance for this. So we have our pressure at 5 minus our pressure at 4 over our density plus our potential energy difference, our height at 5 minus our height at 4. And we're just going to set that equal to our non-flow work per mass. Right off the bat, we know that our pressure at the 5th position is going to be equal to 0, just like before, because it's at the top. And we know that our height is going to be equal to 0. So in order to solve this equation, we're going to expand our pressure 4, and that's in the negative, so you have to be careful of that. So it's a negative rho gh, 1 meter, over our density plus our g times, now here's tricky, it's negative, and we know it's minus 10 meters up, so that's going to turn into a positive 10, and that's going to be equal to our non-flow work per mass. So we have these cancel, we have negative 1 g plus 10g, it's going to be equal to our non-flow work, so that's 9g is equal to our non-flow work per mass. All right, so we have both parts of our power equation. So just to write it out, we know that power is going to be equal to our mass flow rate times our work, non-flow work per mass. So we're just going to work per mass. Okay, so now we have to be careful, because what we found before on this page was our volumetric flow rate. So in order to convert that to a mass flow rate, we're going to have to do that number times density and then multiply that by our non-flow work per mass. And that's how we're going to find our power. So we have all the numbers, just plug it in. So we know that power is equal to density times, say that area and that velocity times the non-flow work per mass. So finally, we're going to plug in our numbers and say power is equal to density times that 0.051 meters squared, area times our square root of 18 g meters per second, our velocity, times our 9 meters times g. And that is our final power equation. Okay, so we know our power that's required for 100% pump efficiency. Now, the next part of this question is, if the pump is perfectly insulated and transfers no heat to the water, is a chiller necessary to keep the water at the same temperature? And the answer to that question simply is yes, the chiller is actually necessary. And that's actually because of this pump. So and X amount of power is coming into the system via this pump right here. So the chiller is basically needed to take that same X amount of energy, X amount of power out of the system. So that is why the chiller is necessary.